This meeting is being recorded.
In section 11 of chapter 13, we're going to be introduced to these types of compounds that are referred to as thiols and also sulfides. So both of these compounds have sulfur contained in them, and it's noted here that sulfur appears just below oxygen in the periodic table. So a lot of times we'll see compounds very similar to alcohols in the sense that we could substitute a sulfur in place of the alcohol, and we could see what we refer to as an analog of an alcohol with a thiol group in place. So notice it ends in OL, just like alcohol. So that's one way to remember the difference between a thiol and a sulfide. A thiol, if you were to replace that sulfur with an oxygen, will look very similar to an alcohol. An older terminology that's used is sometimes referring to these thiols as mercaptans, because certain compounds that contain sulfur can be used to capture mercury. So there's a full explanation of the nomenclature of the past for thiols in your textbook, but we can see this similarity between thiols and alcohols. So this prefix is sometimes used, we'll see, right? So this mercapto group, instead of being named as the parent, we have the alcohol as our parent. An alcohol functional group would have a higher priority than a thiol. So we would name this SH as a substituent. So again, commonly you'll see this would be on our carbon 3 here, right? If we number this based on the alcohol, highest priority being 1. So we have a 3-mercapto, 3-methyl-1-butanol here. And as mentioning previously, these compounds can be used to capture mercury and treat mercury poisoning. So some uses and some common concepts about thiols and sulfides. Thiols are known for an unpleasant odor. Skunks, their spray, uses thiols as their defense mechanism. Commonly in your natural gas, if you have that at home to heat your home, methane thiol is added to methane so that it can be smelled. So that smell, when you have a gas leak, if you ever do, is not the methane itself, but rather a thiol methane. There's also this ion here, this hydrosulfide ion. This is noted as a strong nucleophile, but it's a very weak base. So therefore, HS would only promote substitution, SN2 mechanisms, rather than an E2 mechanism. So we should keep this in the back of our minds. If we ever see hydrosulfide ions in use, they would function as a nucleophile and not as a base. So when we describe thiols and sulfides, we can classify them as either primary or secondary, and that's what we see here. So a primary thiol is being synthesized using an SN2 reaction with sodium thiol here and an alkyl halide. So we see our 1, 2, 3, 4, our bromobutane is being reacted with this sodium thiol, and the substituted product is what we form over here. We can also accomplish this with our secondary substrates, as you see down here. And that same mechanism is utilized, that SN2. So what we see here is thiols can be oxidized to disulfides using our elemental or bromine rather here, Br2, under basic conditions. So we have our two thiols, and again, we have basic conditions with our Br2, and the whole mechanism is shown down below here. But what results from two thiols would be this disulfide product. So take note that we have our thiolate ion that would function as a nucleophile. We have this SN2, this nucleophilic attack from the thiol of our molecular bromine. And then this is our leaving group here. So then we have formed this complex here, this thiolate, and then a second thiolate can function as a nucleophile now, and then we have another SN2 attack and another bromine leaving group. So our final product would look like this after two subsequent SN2 reactions. So we can also interconvert between thiols and sulfides. So we saw the mechanism of action to go from a thiol or two thiols to a sulfide, or rather a disulfide. But let's look at how we can have a reduction occur. So we oxidized our thiol to become a disulfide. Now we will reduce in this process. And we know that when we add bonds to hydrogen, that's commonly a sign of a reduction. Whereas if we add bonds to oxygen, or in this case sulfur, we would have an oxidation. So we use HCl and elemental zinc, and we can interconvert by reduction to create these thiols from a disulfide. And it's noted down here that that would follow a free radical mechanism. And of special note, within proteins, there is disulfide bonds that are commonly seen, and proteins rely on this bonding being easily broken and made to take on their functional form. So you may see something like that in biochemistry. So let's review again some of the nomenclature and what we refer to as analogs. So we mentioned that thiols are analogs of alcohols, but sulfur analogs of ethers are called either sulfides or thioethers. So what we see here is with oxygen, we have diethyl ether. And with a sulfur atom in between two alkyl groups, we now have a diethyl sulfide. If we have a more complex parent, sulfides can also be named as a substituent. For example, we have our 1,1-dichlorocyclohexane is our parent here, and we would name, this is our carbon 1, so on carbon 4, we have this methoxy group, right? OCH3. So that's where that 4-methoxy substituent comes from. Similarly, we can name a methyl thio group on our carbon 4 here. So the same way that you would plug in methoxy, you would plug in methyl thio. But notice that the YL suffix is retained when we name a methyl thio as a substituent. So if we continue here, we can see that sulfides are, in general, prepared by that nucleophilic attack of a thiolate on an alkyl halide. So this is the same mechanism that we saw before with our disulfide, or similar mechanism rather to what we saw before with our disulfides, utilizing an SN2, a nucleophilic attack and substitution reaction. But instead here, we have our final product of a sulfide now. So we have our sulfur in the middle and two alkyl groups instead of the disulfide that we saw earlier. And it's reminding us to note that the thiolate is formed by deprotonation utilizing basic condition. So you should note that sodium hydroxide is used in this process. So here's, again, the full reaction mechanism. Once we have our sulfides formed, they can undergo similar, or a number of reactions rather now. So we can have an SN2 substitution using our sulfide. So here's our sulfide that we looked at how to form. Now this is reacting, and we can form, we can perform a substitution and we can find a product is formed with a strong alkylating reagent, and we can add an alkyl group onto our sulfide, and using a variety of nucleophiles, we can perform a reaction like this, where we perform the substitution, and our sulfide is part of the intermediate product. So sulfides can also be oxidized, and we can form sulfoxide, so that's what we see here, or a sulfone product. So the sulfone product has two of these S-double-O bonds found within it. So again, sulfides can undergo multiple reactions to form either sulfoxides, sulfones, or alkyl sulfides. And the last type of reactions that we'll look at here are where we form sulfides that can be oxidized, rather. So the sulfides can form these sulfoxides or sulfones, and these reagents here can be utilized to perform these reactions. So we have this methylphenyl sulfide, and we have a methylphenyl sulfoxide. Down here, we also have hydrogen peroxides that can be utilized to form a sulfone. So depending on what product you want to form, whether a sulfoxide or a sulfone, you could use something like the sodium metaperiodate, or we could use hydrogen peroxide. And you can see here that both of these structures have resonance structures, resonance contributors. So they are stabilized through resonance. And we're given some details here about the SO double bonds. And now they have very little double bond character, and they actually have more of a single bond character, as shown through these resonance structures here. So they would function more as a SO single bond due to this poor overlap. And on this last slide here, we should mention that DMS and other sulfides, in addition to dimethyl sulfide, are easily oxidized. Therefore, they make very good reducing agents. So in this reaction we see here, this ozonolysis utilizing ozone, this ozonide complex is created here as an intermediate product, and then it's subsequently reduced using this dimethyl sulfide. And our DMS is then oxidized to DMSO.